Hello everyone. I hope you're doing well. This channel delivers videos that promote the importance of mathematical modeling techniques. Currently, I am explaining the Collatz operations introduced in this study. In this video, I show, through simulations based on the rate of change derived from the Collatz operations, that the iterative calculation values probably decrease toward 1. In the previous videos, I showed that natural numbers can be distinguished by the differences in the types corresponding to Collatz operation A, Collatz operation B, and Collatz operation C. Table 1 shows the classification of odd numbers based on the operation types when the Tytrope equation, or TW equation, is y equals 3x plus 1. Table 2 shows the general equations for these classifications. According to these equations, when the total number of Collatz operation A is taken as 100%, the occurrence proportion of each operation type is 50% for a double prime arrow C, 25% for A prime arrow B, and each 12.5% for a prime arrow A prime and a prime arrow A double prime. Similarly, when the total number of Collatz operation B is taken as 100%, the occurrence proportion is 50% for B arrow B, and each 25% for B arrow A prime and B arrow A double prime. Next, Table 3 shows the classification of operation types for even numbers. Table 4 shows their general equations. According to these equations, when the total number of Collatz operation C is taken as 100%, the occurrence proportion is 50% for C arrow C, 25% for C arrow B, and each 12.5% for C arrow A prime and C arrow A double prime. Reorganizing the results by taking all natural numbers as 100%, the proportions of each operation type are shown in Figure 1. The proportion of Collatz operation C is 50%. The proportions of Collatz operations A and B are both 25%. Because Collatz operation C is dominant, the iterative calculation values are expected to gradually decrease. These proportions were determined based on the presence proportions of even and odd numbers within the natural numbers. Therefore, a natural question arises. How are these proportions related to the proportions of operation types that actually appear in iterative calculations? Figure 2 compares the proportions of operation types classified for all natural numbers with the proportions of operation types that appeared in iterative calculations for n0 equals 27 and n0 equals 100,000. Here, standard refers to the proportions of operation types for natural numbers. We see that the proportions of corresponding operation types take similar values. This suggests that in the iterative calculations of the Collatz conjecture, the operation types for odd and even numbers are selected in a manner roughly proportional to the proportions of odd and even numbers in the natural numbers. The reason the two sets of proportions do not match perfectly is that the calculation values generated by the Collatz algorithm vary, depending on the chosen initial value, exhibiting different behaviors. A similar discussion applies to other TW equations. Figure 3 shows the occurrence proportions of operation types for y equals 5x plus 1. Figure 4 shows the occurrence proportions for y equals x plus 1. Note that only the occurrence proportions for y equals 5x plus 1 differ from the others. For details, please refer to the supplementary information of the first paper. Based on the determined proportions of operation types, I performed simulations of the iterative calculations. In this study, I constructed two types of dynamic models. These models assume that the iterative calculations proceed step by step according to the Collatz operations. Therefore, the calculation values were obtained by considering the occurrence proportions and rates of change of the Collatz operations at each step. In Dynamic Model 1, different operation types were treated as a single category and the natural numbers were assumed to change according to the average rate of change. Using the proportions and rates of change shown in Figure 1, the average rate of change alpha for the TW equation y equals 3x plus 1 is given as follows. Because the average rate of change is less than 1, this essentially means that the natural numbers decrease with each application of a Collatz operation. Similarly, the average rate of change for y equals 5x plus 1 is given as follows. Since this value is greater than 1, the iterative calculation values are expected to increase. The average rate of change for y equals x plus 1 is given as follows. Because this value is sufficiently smaller than 1, the iterative calculation values are expected to decrease reliably. Using the determined average rate of change, I performed the calculations. Here, each time Collatz operations a double prime, B, or C are executed, the number of operations increases by 1. Let the initial value of the natural number be n0, the number of Collatz operations be n sub c, and the calculated value in the Collatz operation at any n sub c be n bar sub n sub c. Then, the change in the calculation value n bar sub n sub c divided by n sub 0 based on the average rate of change is expressed by the following equation. It should be noted that the calculation value is expressed in a dimensionless form by dividing by the initial value. Figure 5 shows the relationship between n bar sub n sub c divided by n sub 0 and n sub c for the TW. Equations y equals 3x plus 1, y equals x plus 1, and y equals 5x plus 1. For y equals 3x plus 1, the dimensionless calculation value decreases exponentially from 1 as n sub c increases and becomes close to 0 when n sub c is around 25. In Collatz operations a double prime, B, and C, the number of iterations n sub are performed in one trial is 3, 3, 2, and 1 times, respectively. Considering these values together with the proportions of each operation type, the average number of iterations is 3 times 0.125 plus 3 times 0.125 plus 2 times 0.25 plus 1 times 0.5 equals 1.75 times. Rounding this to the nearest integer gives 2 times. This value of 2 is considered reasonable. For example, when n0 equals 27, the total number of iterations n sub are total until the calculation value becomes 1 is 111, and the total number of Collatz operations n sub c total is 53. When n0 equals 1,010,101,010,101, the total number of iterations is 247, and the number of Collatz operations is 123. Thus, in actual calculations, the total number of iterations is approximately twice the number of Collatz operations. In Figure 5, the dimensionless calculation value becomes nearly zero when the number of Collatz operations is around 25. Therefore, we use equation 1 to determine the number of Collatz operations required for the calculation value to become 1. 4n0 equals 27. The calculation value becomes 1 when the dimensionless value is 0.0370. 4n0 equals 1,010,101,010,101. The dimensionless value is 9.90 times 10 to the power of minus 13. Substituting these values into equation 1, the number of Collatz operations becomes 16 operations for n0 equals 27, and 133 operations for n0 equals 1,010,101,010,101. Since we assume that the total number of iterations n sub our total is twice the number of Collatz operations, the estimated total numbers of iterations are 32 times and 266 times, respectively. The actual total numbers of iterations are 111 times and 247 times, respectively. 4n0 equals 27. The predicted value from equation 1 differs significantly from the actual value. This is because 27 is a transiently rapidly increasing number, whose calculation value increases dramatically before eventually reaching 1. On the other hand, for the non-increasing number 1,010,101,010,101, the two values are close. Table 5 compares the actual number of iterations with the number of iterations required for the calculation value to reach 1. According to equation 1, for a wide range of n0, the two values differ greatly when n0 is small, but they become nearly identical as n0 becomes large. This is because as n0 increases, the overall behavior of the iterative calculation becomes dominated by decreasing behavior. Figure 6 shows the relationship between the total number of iterations n sub our total and the initial value n0. For most values, the number of iterations gradually increases as n0 increases. Transiently rapidly increasing numbers exhibit extremely large numbers of iterations. The dashed line in the figure represents the calculated line for the number of iterations obtained from equation 1. For initial values that are not transiently rapidly increasing numbers, the number of iterations closely matches the actual behavior. This indicates that equation 1 can be used when checking the validity of a proof of the Collatz conjecture. As shown in Figure 5, for y equals x plus 1, the dimensionless calculation value decreases rapidly as n sub c increases. This is because the average rate of change alpha is sufficiently smaller than 1, with a value of 0.4375. The iterative calculation value smoothly becomes 1. For example, when n0 is less than 100, the number of iterations is always within 100. As shown in the following table, for various values of n0, the iterative calculation values take values very close to those predicted by equation 1, unlike the case of y equals 3x plus 1. This is because for y equals x plus 1, the calculation value steadily decreases to 1 for all initial values. On the other hand, as shown in Figure 5, for y equals 5x plus 1, the dimensionless calculation value increases rapidly as the number of Collatz operations increases. This is because the average rate of change alpha is greater than 1, with a value of 1.1875. In fact, for y equals 5x plus 1, the iterative calculation values diverge from many initial values. In Dynamic Model 2, the proportions and rates of change of individual Collatz operations shown in Figure 7 were used to calculate the rates of change for odd and even numbers appearing at each calculation step, according to the network shown in Figure 8. The sum of these values was then taken as the iterative calculation value. The results are shown in Figure 9. In this model, the characteristics of the initial value are reflected. Therefore, for y equals 3x plus 1, the dimensionless calculation values decrease from the beginning when the initial value is a natural number of type A prime, a double prime, or C. In contrast, when the initial value is a natural number of type B, the dimensionless calculation value increases once and then decreases. Figure 10 shows the linear extrapolation obtained by applying the least squares method to the decreasing part of the dimensionless calculation values in Figure 9. As in Dynamic Model 1, the dimensionless calculation value becomes nearly zero when the number of Collatz operations is 25. Figure 10 plots the total number of iterations n sub are total obtained by varying n0 from 1 to 10 to the power of 12 using the TW equation y equals 3x plus 1. The number of iterations tends to increase as n0 increases. Even for very large values, such as n0 equals 10 to the power of 12, the calculation value becomes 1 in only about 400 steps. As was shown in Table 5, even when n0 equals 10 to the power of 100 plus 1, the number of iterations is at most 2,467. These facts suggest that even for extremely large initial values, the calculation value becomes 1 relatively quickly. In this video, we perform simulations using the rates of change of calculation values in the Collatz operations. As a result, we found that the calculation values decrease. However, this is not a rigorous mathematical proof that the iterative calculation values in the Collatz conjecture always reach 1. The discussion here is only a reference based on the results of mathematical modeling. A rigorous proof will be presented later using the Collatz-Rope model. That concludes today's talk. I look forward to seeing you again in the next video. Until then, take care.